Air traffic controllers monitor the space around an airport by keeping track of various airplanes' location and movement using a radar screen like the one shown below. At the center of the grid is the air traffic control tower. The radius of each of the surrounding rings increases by 5 miles. When an airplane enters the tower's airspace, it is seen on a grid by a bright point called a screen pixel. So, number one, an airplane is 15 miles from the tower. Show all possible locations of the airplane. Okay, so we would go out, like each circle is a radius of 5. So, we would go out 3 circles, and then anywhere on that circle is 15 miles from the tower. All right, so number two, because this information alone is not enough to locate the airplane, controllers also mark locations with an angle that is measured counterclockwise from due east. Plot a point that represents the location of an airplane that is 15 miles and 2 pi over 3 radians from the tower. All right, so we already know 15 miles is that third circle. If you guys remember the way the angles, the special angles were that we worked with. Oops, sorry. That one is pi over 3, and then this would be 2 pi over 3. So the airplane should be located at this point. All right, we'll pick up with number 3, the lesson tomorrow. Okay, and so when we travel in air or in the sea, the rectangular coordinate system sometimes isn't efficient enough to be able to locate a coordinate point. And so we are going to start talking about a brand new coordinate system that's based on circles, and it's called the polar coordinate system. And so instead of using the rectangular coordinate system where you go over a certain amount and then up or down a certain amount to get to a point, we're actually going to go straight to the point. So the polar coordinates tell you the distance that you travel and then the angle that you travel that distance. All right, so the polar coordinate system only has one axis, and it's this axis that's pointing directly to the right. It's called the polar axis. And instead of the origin, the polar coordinate system, the point that we typically call the origin, is called the pole. Right. So this vertical axis is just for reference. And so you're given two coordinates. One is r, which is the distance from the pole, and the other is theta, which is the angle that ray or that r value is taking. And one thing that is really cool about polar coordinates that we can't say about rectangular coordinates is the same point can be represented different ways. And that's one of the things we're going to do today. All right, so the first thing we're going to do is plot some polar coordinates. So this grid has 3 angles labeled. So I'm going to go ahead and label more of them. So the angle straight to the right is 0 radians. Straight up is going to be pi over 2. Right, and then this is going by twelfths as we go around from 0 to pi. So the first one on each side of it, axis, is not going to be labeled. It's not really a special point that or a special angle that we've been talking about. That says 3 pi over 2. That really didn't look like it. So I hope you guys remember these from the unit circle. We are still going to be using these same angles And we're also, starting tomorrow, still going to be finding sine, cosine, and tangent of those same angles. But today, we're not getting into that. Today, we're just going to plot some points. And so the R value is 2, which means we're going to go out to the circle, but labeled with a 2. And then we're going to go to the angle, labeled pi over 3, and that is point A. All right, B, we're going to go to the circle labeled 1, and then we'll go to the angle 3 pi over 2. All right, for C, we're going to go all the way out to circle 3, the outer circle, and then go to 4 pi over 3, and that is angle C. And then D is the first one where we have a negative coordinate, and so negative coordinates definitely make this more difficult. But we're still going to go to 2, the circle with 2, and instead of rotating pi over 6 this way, we're going to rotate in the negative direction, which is the clockwise direction, and it is going to be here at 11 pi over 6. All right, let's look at example 2. I'm actually going to start with D on this one. So on D, the R is negative, and so a negative R, instead of starting the circle 2 to the right, it's going to be 2 to the left. So we're going to start here. And then we're going to rotate around 5 pi over 4. So 5 pi over 4 is this angle. And so normally that rotation would be this much from 2. So we're going to do that much, but we're going to rotate from negative 2, and we're going to end up right here. All right, now let's do the other angles as well. So for A, we're going to do 2 and then pi over 4. Well, that's the exact same point we just did. All right, and then for B, we're going to do 2 and then negative 7 pi over 4. So 7 pi over 4 is this angle. So we're going to rotate this much. Sorry. Oh, not that much. Sorry. This much. But we're going to do it in the negative direction. And it is taking us right back to that same point. All right, so you probably see a pattern forming here, but let's go ahead and look at C. So C, we have 9 pi over 4, which is more than 2 pi. So it's going to be a full rotation and then some more. So let's figure out how much more by taking 9 pi over 4 and subtracting 2 pi from it. So that's the same as 9 pi over 4 minus 8 pi over 4, which is going to be pi over 4. So it's that same point again. So we had 4 different representations for the exact same coordinate point. And that happens. You can do that with polar coordinates. And that's the last thing we're going to talk about today, is representing these points multiple ways. All right, so for number 3, we're going to plot that point first. So 3 and then 5 pi over 6 should fall right here. However, that is not the only representation for that coordinate. So I'm going to give you over here on the side like a generic form, like what we're doing to get these different representations. And so one thing you can do is do what we just did on part C, where we can take and leave the R exactly the same. So if it's 3, it stays 3. And then we can take the angle and subtract 2 pi from it. So for this particular problem, it would be 3, and then we would take 5 pi over 6 and subtract 2 pi. Well, I'm not going to write 2 pi as 2 pi. I'm going to write it as something over 6. So if I want to get 2 pi, I would take 12 pi and divide it by 6. All right. And then to get the final answer, we'll have the 3, and then 5 pi minus 12 is negative 7 pi over 6. Right. So what happens with this point is you go out to 3 and you rotate 7 pi over 6 in the negative direction, and it takes us to that same point. All right. Another thing we can do to get a another representation is do the opposite of r. So if r is positive, change it to negative. If r is negative, change it to positive. And then take theta and just subtract pi from it. So for this example, it would be -3. We do the opposite. And then take the angle and subtract pi. So for a denominator of 6, pi is going to be 6 pi over 6. And so that would be -3 negative pi over 6. All right. So what that means is we would go to -3, and then we would rotate pi over 6 in the negative direction, which is the clockwise direction, and we would end up at that exact same point again. And then the final way we can do another representation is to do the opposite of r and then add pi. All right, and so this would be the -3 and then 11 pi over 6. So that means we would go to -3 and rotate 11 pi over 6, which takes us to that point again.